Okay, Mike, are you going to introduce our speaker or shall
I can, I didn't write anything
I?
down.
Well, I printed some stuff out.
Okay.
Perfect.
All right, so I did my homework here. Thomas Helfer, if I'm pronouncing that right, is a computational physicist. I know you didn't write astrophysicist.
Yes,
so
yes,
you're a
yes,
little
yes.
broader. Working on deep learning in physics, postdoc at Johns Hopkins after PhD from King's College in London. Postdoc here at IACS,
Yeah.
working with Mike.
Yes.
Although several people have commented, we don't see you over in the astrophysics group enough, so.
Yes,
chop,
yes.
chop. But with that, we'll get started.
Perfect. So I hope, yeah, I moved everything, so you should, that's the most I can, I removed all the non-participants. But yeah,
That's good.
good. Well, let me talk about how to apply deep learning for astrophysical simulations and observations. So I'm going to start with the part where, are you refusing to listen to me? All right. You might have been tortured with I mean, it's lots of astrophysicists here, so I wonder what I'm saying here, but for the non-astrophysicists, you might have been tortured by the gravity in high school. And however, the full story came a few years later with that handsome fella. And
We didn't do that in my high school.
Huh?
That wasn't in my high school.
And he wrote down here the Einstein field equations, which describe gravity significantly better than what Newton did. And however, if you actually want to simulate these ones, you have to write them in a form where time and space is explicit. Here it is not. That took another roughly 50 years, 40 years roughly until they filed this formulation. And this is the ADM formulation of general relativity. And if you just throw it in a computer, you will painfully notice that it will just blow up because it's highly unstable. That took another 50 years to find this formulation. This is what we are using, the BSSN formulation, to actually simulate general gravity in a computer fully. And it's a massive pain. It's very hard.
So Thomas, before we go too far, there's something in the chat. Check that and see if
yes.
somebody's saying they can't hear or
So
something.
yeah, absolutely right, Han. Yes. Well, I think. Oh, no, they should be fine.
Yeah, okay, so we're good.
Okay, good. You can hear, perfect.
Thanks.
All right. So just to give you a high level overview of what happens if you do, here's a simple binary system. And in just normal gravity, with Newtonian gravity, nothing will happen. However, if I now switch over to Einstein, what will happen is these objects will get closer and closer and closer. They will merge, and as they do, they will radiate out gravitational waves. And these are really cool because these ones we can potentially measure. Here's now. Can you allow participant to unmute for question? Yes, of course. I just don't know how
Is
to do
it admin on as well?
I don't know. Chelsea is.
I thought Ann was on.
Chelsea is the host,
Chelsea is
so
not
she should
around,
be able to
unfortunately.
change the,
So we just
settings.
have an eye out for the question in the chat. And so
I'll tell you, I'm gonna log in on my phone, and as questions come up, I'll answer.
amazing. All right. So this is one of our simulations of two black holes coming closer and closer. And on the bottom you see the, let me fix one around. At the bottom you see effectively the gravitational wave signal. And at the bottom you see the gravitational wave signal. And on the top you see the no worries. No worries. And you can see the two black holes going closer and closer. So just a reminder, black holes actually don't have a surface. This is just indicates the point of no return. And now we see we're just a few milliseconds before merger. And they are close enough such that they form a common horizon. And now merge and create a new black hole. This black hole now is highly perturbed and now rings down effectively. And so this process we hope to measure. You now can see the gravitational waves that are being radiated out in that specific process. Now these travel for infinitely, for very, very long. And my path to Earth. So say if you're a circle of stones, like thrown above and a gravitational wave passes through, you will see the following. We'll see first this circle of stones be deformed in this specific way. And that will allow you to measure the gravitational wave. So unfortunately, this deformation is super tiny, right? This is not like, you're not going to see any stones moving. This is a fraction of the radius of an atom. So what you have to put is you have to be like super sensitive lasers that are able to measure these specific distances. And there's one of these devices in Italy. You can see here, you shoot out, this is the central facility in the center. They shoot out lasers back and forth. They get reflected at the end and then come back. These are vacuumized tubes, so the lasers move unperturbed through these tubes here. There's also here one in Livingston in Louisiana. And these are hypersensitive objects. Like they measure everything from waves hitting the American continent, from wind blowing on the trees and slightly pulling on the ground. These are unbelievably sensitive. Every earthquake, even rush hour traffics, the city far away can perturb this. So these have to be in very isolated places here. This one, there's another one in Hanford. This one I was able to visit. And it's very, very remote. And in the road below, there's actually a nuclear trash, not recycling, like where they put nuclear trash. So if I glow a bit in the dark, don't mind me. And so there's, of course, you can see there's the environmental shield out of concrete, and in the inner part there is, of course, the tube, the vacuumized tube with the laser. At the end, there are these unbelievable mirrors that are super seismic isolated. And I mean, just to give you an idea how sensitive are, these are 40-kilogram mirrors, and quantum effects of the mirror have an effect on measurements. Like, quantum effects typically are not relevant for 40-kilogram objects, but these are so sensitive that they absolutely are. This, of course, resulted into a Nobel Prize, the first measurement of a gravitational wave. And we're very confident that this is just not just like a graduate student running by the detector, because we have multiple detectors measuring at the same time. And that's extremely important to have this confirmation. Now, how do we know from just looking at these two signals from these two detectors that this is roughly, that has a distance of roughly 410 megaparsecs, and each of the black holes have roughly 30 solar masses. How do we know that? 410 megaparsecs, just to give you an idea, is roughly 1.3 billion light years away. So when these black holes merged, there was not much on Earth, just some microbacterial life, maybe at most. I'm not sure, I'm not an Earth person, but I think that's what was happened there. So what we do a bunch of computer simulations. We produce a bunch of gravitational wave signals, and then we compare them effectively with our signal. So this is just a classic inverse problem in physics. And then we figure out what roughly the parameters are. But we're still really at the beginning of the journey in gravitational waves. We literally did our first flight here. A really easy way of eliminating seismic noise is just taking whatever we have and shooting it into space. So that's one option that's being done. The other option that we're for ground-based is just whatever we have and make it 10 times bigger. That's also a very good option to get much better gravitational wave measurements. And so the future in gravitational wave is super exciting, because we're going to have these extremely order of magnitude more sensitive detectors that just blow everything that we have out of the water. I think we're going to be able to measure almost every observable binary black hole merger in the universe. It's truly impressive. Here, but you can see a comparison between LIGO A+, which is a current, slightly upgraded version of the current detectors, and what the signal would look like for the next generation detectors. So it's a massive difference. And currently what we have is like, we have some model noise that could create biases, but doesn't assume the detector noise. And roughly at the moment, they're not a problem. We're still mostly bothered by detector noise. But
LIGO A plus is current?
no, this is a strongly upgraded version of LIGO.
And what's Cosmic Explorer?
So this is a next generation one.
Okay.
So that's what we yeah. And so for the next generation, we potentially have this gap where, okay, we might get better just thanks to Moore law, if that even goes on. But so we really have, and then we have potentially this gap, which is effectively thrown out money because these are $1 billion investments in scientific investments, and we might not be fully able to use this data. That would be fairly terrible. So that was the motivation, at least for my work in machine learning. And why machine learning, specifically deep learning, is lots of the GPU architecture, or like HPC architecture, is now being moved to GPUs. So there's more and more GPUs available, and I want to use them, and also want to use them efficiently. And of course, deep learning is a very natural choice for that, to be able to do that. But for that, I need a feasible algorithm to use this in my simulations. And so there was this cool paper. This was my first idea when I was still at Hopkins. I was like, oh yeah, it's a super simple paper. What they do is they study here. There's a big black hole and a tiny black hole, which effectively on a space-time looks like just a big black hole, because a tiny black hole doesn't do too much. If you see, this is an error estimate of the numerical error of my simulation. And what I could do now is, well, this looks almost like a single black hole. Since I know the evolution of a single black hole, I can just make a time step using my single black hole, compare, and just use that error estimate from the analytical solution to then correct for my numerical simulation. And it works really well, but it's very specific to this situation where your simulation is close to to analytical solution, right? Which is very rare. Most of the time they're not. So it was so frustrating, because like, it's such a cool, easy method. Like maybe, I mean, my hope was like, maybe I can do this. And maybe, I mean, what I could do is say, I have my simulation, and it's, well, I'm do my standard evolution, get to my next time step. But now what I just use is a network that will just go over and has learned this correction from data instead of this analytical estimate, and just do that. I was like, great, let's get coding. So I threw in a demo together. And so here I purposefully took like a advection equation. That's the easiest equation you can do. I purposefully used a terrible evolution scheme. And you can see red is the exact solution, blue is my numerical solution, and just purposefully is terrible. Just it's nice to have something that is very visually terrible. And then I learned the difference between at every time step what the error might be, and of course it works very well. But this is an extremely easy example. And then I presented the idea here for the fellowship position. I was very excited to get it, and I was like, yes, now I can get going. And
it does start to diffuse eventually, the ML one.
Yeah, it's not perfect. Yeah, it's much better than the other one. And yeah, it is a super easy example. And GR is much harder because, first of all, we're 3D, and GR not only has one field, it's had 25 fields. It's more than I fit on my screen. So like, it is a much harder problem. So I got the fellowship, I was here, and like I got going. I started, first of all, producing the data. I generated data, then I had to create a pipeline to do this, to then put it into Python, and then create a Python interface that took the trained network and reintegrated it in my PDE solver. And I was like, oh yeah, this is all a good idea. It's fantastic. And then I was finished. Now I was there. Like I created effectively a cruise ship. And like I was there with this humongous thing that barely was able to move, and I wasn't able to do anything with it just because actually what I needed is an engineering team. And turns out I'm a poor academic that doesn't have money for an engineering team. So I was forced to scrap my ship here and start effectively from new. So after scrapping, I had to come up with new ideas. And well, I figured that maybe ideas I didn't have any, but problems I had many. So I started with problems. So one thing that our code does is adaptive mesh refinement. And there's a question.
Yeah, he says, how do you know that the neural nets which you've trained on the analytic test problem will give an accurate correction on more general problems?
Oh, well, that would be testing on more general problems. And I think I didn't come that far because it was such a cruise ship, and it was really hard to test everything or do anything with it. So in the end, I scrapped it. But I will come back to the generalization question in my corrected version, and there I will talk about generalization. So first of all, adaptive mesh works. It's really cool. You say like, oh, I have a thing there, that there's thing happening. Just mark it down and throw in a new grid. So I do some interpolation, take the low resolution grid and create a higher resolution grid. Again, I can go there, mark the grids. Maybe there's something in the middle of that thing is happening. I mark it again and create another grid, do another set of interpolation and create a new grid. And there, maybe in the center, I can do it again. I can do this infinitely often as long as I have enough memory. And EMA is amazing. It's such a simple technique. It saves so much compute by just not putting fine grids everywhere. It's truly amazing. However, what it does a lot of interpolation to create from lower resolution to higher resolution grids. And if you talk with machine learning people, this is just an example of how much interpolation we sometimes have. This is a really cool simulation. This is a black hole torus. So it turns out if we are not just in boring 4-dimension, but you can say go do 5-dimensional general relativity, black holes can be toroidal. And there's a solution for that one. They are unstable. So if you simulate them like this, they become unstable and just form a normal 5-dimensional boring spherical black hole as we know them. But this was to show just like how much regrading is, just to emphasize that it is indeed a problem. So super resolution is a very well-known field, and effectively what I'm doing, this is actually kind of a good solution for it, right? Like, and so, however, there's one drawback. I need lots of high resolution data. Turns out, like if I want to have a better simulation, and what I need to do to get better simulation is run more better simulations such that I can do that. And maybe that might have worked if it generalizes well, but turns out I'm still a poor academic, so maybe not. Is there any other options? Maybe a magic loss that I can use to not use a high, high resolution labels? Well, let's go back to the handsome fella here, and let's look at his equations again for a second. And I'm not going to ask you to look too hard because they're horrendous. But in general, these equations have these ones are the important equations in that they have the form a partial time derivative, something is equal to something. And they do the following. They take a current spacetime at time t equals 0 and transform it to a time t equals 0.2. So these are just the evolution equation. They tell you how spacetime is gonna move. But then there are these weirdos. These weirdos don't have any time derivative. So what you actually can do with them is you can just apply them to one block of spacetime you currently have and check if you take the left-hand side and the right-hand side, and in ideal case, they would be perfect. Left-hand side and right-hand side would perfectly match. But in numerical cases, they don't. So you get a number of how well this spacetime is consistent with general relativity. That is typically a massive pain for all of our simulation to keep this number small. But here it's and this is it's useful at least to tell if something is going wrong or not. But now what we can do here is we just take this horrendous equation and we throw them into a loss. And this is practically a magic thing that saves me, poor academic, from generating high resolution data in that, because I can just use that very complex loss instead. Use effectively a bit my knowledge of general relativity to solve my problems. Of course, I coded it up in a GitHub repository. If you feel brave, and yes. So maybe let's give you just a small overview of my model. I'm still I'm still using some classical interpolation to first get my first approximation. And then I take this approximation, which then I use a CNN. And CNNs are especially perfect because Einstein gives me a lot of symmetries. And especially in the Cartesian coordinates in this grid set I have, I get automatic translational symmetry. So that's effectively already encoded in a convolutional network. So I get that for free with a convolutional neural network. Now with that one, I can estimate an error, a correction that I'm going to add up on my initially interpolated one, and effectively can then effectively correct my interpolation.
Thomas, does your loss function have a notion of conservation?
Yeah, so effectively, what these equations are, they are like a hardcore version of energy and momentum conservation. They are even more potent than energy momentum conservation. That energy momentum typically is global, but Einstein hates global things, so everything is local. So it's actually every pixel or every tiny space-time has to fulfill these equations. So this is even a significantly stronger constraint.
But that's normally how it works in AMR, right? When you interpolate to a finer grid, you do so conservatively, right? So you don't create any new mass, for instance.
Yes.
So when you're doing this upscaling, are you conserving when you?
So no, in this case, we don't conserve this one. Okay. But there's more to it. There's more to it. So so yeah. So effectively, yeah, we now created this correction. Yeah. And now, of course, this is pretty cool because how AMR works is just like it splits up the grid on several nodes, and indeed, like what we find is that we can just run separately on each node. This is pretty cool because we don't need to add any interaction between cores. So this is what I wanted to say with that is that whatever this specific model was made in such a way, at least everything is such in a way that we can easily just pop it into current state-of-the-art codes without ripping too much out, at least. But yeah. All right. So let me just go for the performance here. So what we find here is that so first of all, this is a normalized performance, right? Using my specific loss, and the baseline of interpolation is the one above, and the one here in the bottom is the performance of our model. So this is the performance on our model on the simulation per se. So here what we're taking is just a single simulation with one binary black hole. We take the data we learn on that one specifically, and we see on how well it performs, which 90% of the time, that's not what you're doing. So you actually try to, for example, change the mass of the black hole or other parameters. I just looked here at the change of the mass of the black hole and see how it performs. And if you can see, like if I change it 4%, of course, the performance becomes worse and worse and worse the further I go away. At some point, I'm actually worse than just normal interpolation effectively. And so this is pretty cool in a way. So it does generalize. And of course, this is a very extreme case. Like in a normal case, what I would typically do is I put multiple solutions at the distance to learn, and then can generalize significantly easier on the points in between. But it does generalize to simulations. It hasn't, as we've seen, to That's pretty good.
Thomas, you're mainly using this for the interpolation in AMR.
Yes, but there might be also the possibility, which I'm not, which we can talk about, is to also use that then afterwards for the time step.
Right, but you're, just so I understand, your goal wasn't to improve the performance of it, it's to improve the accuracy.
Yeah, exactly. And by that, if you have a better performing accuracy, of course, you
Well,
might.
I mean,
Yeah.
not the wall clock, so this could be slow,
This could be slower potentially, but yeah,
but you're caring about how accurate it is when you.
exactly, yeah. But there's a bit more to it, and I will come back to it in a second. Because there's one really powerful thing that we can do with that one. So first of all, just very fast at looking at the performance of the L1 loss. And here you can see which one you would guess, like one is converging super fast and the other one is converging very slowly. So one is using high resolution label. Fast guess which is which. What's the orange one?
High resolution.
High resolution is the orange one.
No, I think it's the other.
It's the other way around. So
Yeah.
the orange one, the other one is our loss, the highly informative one, which is weird, right? You thought you would incur a cost by using a fancy loss. But it turns out because it's such an informative loss, it has so much information about general relativity built in, it allows the model to converge really fast. In comparison to L1, in L1, you're just like, oh, is this pixel is this pixel the same as the pixel in my data set? And that's fairly simple. But for my loss, it's significant. But in the end, it turns out my loss is also really expensive. So this is the L1, and it's also the baseline. And in the end, because my loss is so hard to evaluate and it's so big, in the end, I'm kinda as fast as L1 at least. Though in steps, I need significantly fewer steps. Now, the more interesting story that's maybe now the one, the relevant is do I get the same thing? Do I get the same solution? And what you can see here is this is in L1. So meaning, so this one here is the baseline, the line, the blue line here, violet line is the baseline. And you can see that my loss brings you towards something that is close to the baseline effectively. That's how I built my model a bit. That's what's happened. However, if I use the L1 loss, I go effectively to 0, which is the ground truth. So this is in a way, we have the following picture now. Turns out my loss has multiple solutions. And as we go, and we have these two solutions. If I just have a random start, I fall in this new alternative solution that is not close to the ground truth. However, the ground truth solution for that I achieve with L1 also exists in LGR. So technically, if I have a warmed up neural network, I can actually just fall into that specific new ground truth solution with no problem. And I did this experiment. I warmed my network on for black hole with one mass, and then applied this warmed up network to something with a bit of a bigger mass, but using my new special loss. And if everything goes well, my network should now converge to 0. And of course it does, because otherwise I wouldn't show you that plot. But yeah, so this was very relieving for me to say, okay, wow, this really works, and I can actually find the real ground truth using my new specific loss. I have to be close enough. So this is a 20% different mass, but if I go a bit too far, I'm not going to find it anymore. So this is the problem. So why is this cool? Well, what I can do now is effectively what ChatGPT does, or any foundation model. These foundation models are powerful because they can use unlabeled data at mass, right? Like you just effectively take all of the internet's data, you let the model stare at it for like months, burn the half electricity grid, and and get something that you can afterwards vary the data fine tune. And so here it's kind of the inverse picture, probably, that this is still a hypothesis given by paper. I haven't actually done it, but this would likely, we have one network that initializes using effectively high resolution data, the network. But then what I can do, I can just use a massive amount of unlabeled data, also smaller, in this case, cheaper simulations, to then just effectively make it more generalizable on a huge parameter space. And so so I can actually achieve ground truth by doing this one. And get that control. Of course, I haven't done that. This is my hypothesis. I need more compute, please, and to do this. But this is likely the picture that we got from that we can likely do using these new losses. The cool thing is that we also found, this more side comment for your question, we don't necessarily need to do interpolation for that, and we can actually just take a normal grid, try to calculate a correction for that grid per se. But yeah. So very excited. Like I did the first ever application of deep learning to numerical relativity. We showed that we can reduce the use of labeled data massively, and it can be something that also can now be integrated in state-of-the-art codes. It's not something where you have to rip down your whole architecture. You can just hopefully use this, and it works. At least that's the idea. That's the hope.
Can I ask a question?
Yes, please.
You did this training where you did one mass and then you ran it on another mass. What if you train on a low resolution stage and then
apply it on a high resolution simulation? So the loss is inherent. There is spatial gradients in that loss. So that wouldn't work terribly well. It works as initialization. That might be a cool idea.
Yeah.
And then you have to retrain.
You still have to once you resolve things though, it should be okay.
After you retrain it, it might be a good enough initialization. You don't maybe need actually. That's also a nice idea of, instead of using effectively as initialization as another mass, you can actually just use a lower resolution one. That would be actually pretty cool if that would work.
Yeah.
That's an easy experiment actually. That's a good idea. All right. Now another very small. Oh yeah, sorry. Questions? Yes.
Can you clarify what you mean by warming up the?
Yeah. So what I'm meaning is I'm just training it. But there's many new messages that I.
No, we're up to date.
Oh, we're up to date. Okay. So what I'm doing to warm it up effectively, I'm learning it on using a high resolution reference effectively, using the L1 loss on. In this case, I'm using it on a black hole, on one black hole mass, and then use the same network, then apply it to a different black hole mass effectively.
Okay.
And so this is the warming up, and so that's why I need at least some labeled data to at least get everything started. Okay.
So GR is like nicely scale free, right?
Yes.
And interpolation is local. So when you talk about changing the mass, I guess you mean you're changing like the curvature relative to the unit coordinate length or something.
You're coming into a point. Yeah, technically it is scale invariant, but in this case, because I have the grids and I break the scale invariance technically, it was just an easy parameter for me to change in a way.
I'm wondering if your network knows about that. Like
that I'm implicitly, that could be that I'm implicitly.
You could put grids at different curvature scales in essentially the same simulation.
Yeah.
And train it repeatedly at those different scales.
Well, you get that for free with AMR.
Exactly, right? Like, one grid looks basically like the next level of refinement, just positioned at the right place in terms of like scalar and vector curvatures and so on. is there some way, yeah, it feels like you have to be able to exploit that structure to like vastly replicate your training data in some way.
Yeah, maybe
right?
maybe you're absolutely right. Maybe implicitly that's what I was kind of doing, in that I was implicitly using partially the scaling. But yeah. So your point is that sorry, I think I don't fully understood your point. Like you saying that effectively that I have to scale invariance, and effectively my grids kind of are just like different resolution, are just scales of different of the lower resolution effectively.
Yeah, I mean, it has to work like that basically, right?
I mean, this would work mathematically, but you always have to think that I work with discretized grids. So maybe, but you may be right, because the scales as the grids become also refiner as I decrease the scale. So maybe there is some co-scaling working, that actually the errors on different levels kind of would look the same. That would be kind of cool. Maybe that is similar. Then actually,
You should be able to look at the AMR hierarchy and see.
if that's, yeah. I mean, it's the same experiment that you are in a way proposed. If like, can I use effectively the lower resolution on the higher resolution one? And that, yeah. So yeah. And but yeah, it's a good idea. Cool. I'm gonna try this. Okay. Any other questions? Because I'm gonna switch now gears a bit, slightly. Okay. So I'm going to switch now to supernovae, so the thing that happens before you have black holes. And so this was also a cool project, and also just to give you a bit of overview. This is current. Wait, I have many movies. This is the view of out of our sky, and every dot here is a supernova, right? You can see, this counts the year of detection. This was 1950s, and now after 1990s, things really accelerate pretty hard, and so this is thanks to lots of undirected surveys that have been built. So you can see the number of discoveries over the years. And so after around the 1990s, things just skyrocket upwards. And this is really just the start. This was gonna be pretty more extreme with some of the upcoming LSSD surveys that will produce. I think currently we're at, Alan, you probably have 100,000-ish observed supernovas, and this one's gonna produce roughly 1 million per year, something like that. Yeah, so it's gonna be a massive increase on supernova data that we have available, because that is very attractive. And so what are we measuring? So how in when we observe a supernova, so you can see here this very bright event happening. This is supernova happening in a galaxy, and what we would measure over several days after it happens is these photometric curves, effectively, which have different averages of different frequency spans, and how they evolve over time. And what this roughly represents here, this is the SED. So that there's in the y-axis the amplitude over that we have time, and we have also the wavelength. So with the photometric modality represents effectively an average of that over frequency with some photometric filters. And we have also spectroscopic follow-ups, which effectively are just a cut through that surface. And this one is all of the information that we can get from supernovae and identify them. Photometric is super cheap, and spectroscopic, because there's long integration times to get each wavelength separately, is very expensive, and only roughly only 1% of all supernovae roughly have a spectroscopic follow-up. So what would be cool now if we can combine these data into one model and enhance the performance we can get from photometric data. So say we take both photometric and spectroscopic data, throw them in one big model that can take both of them and maybe then use the fact that there is mutual information between the both of them to learn something. What we're using is something called contrastive learning, if you have heard of that one specifically. So say we have this very beautiful samoyed, and we pass it through our network, and we get two embedding vectors for them. If I plot them here, it's two-dimensional. Typically, it's like 100-dimensional, these vectors, but two-dimensional. And what I want now is that since they're representing the same thing, namely this beautiful dog, then these vectors should get closer, right? And in contrast, if I then use also this very beautiful baby schnauzer, then I get a different vector. However, this represents a different thing. So I want that they don't get close at all. Yes. So now I'm doing the same thing for the spectroscopic and the photometric modalities. And I get and what I'm using here is roughly 5,000 supernovae from the Zwicky transient survey. And I get some vectors. And of course, I want to take the one of the photometric after I train the data, and see if this actually is something usable. Because the cool thing about this foundation model is like you give them this more generic task, like for example for ChatGPT is like guess this. You blind part of the sentence out, and it has to guess this part of the sentence, or like what comes in the future. And here we're just trying to align these vectors in this space, and hopefully we get some features that then are super useful for us to then do some downstream tasks. And the ones that we're trying is like supernovae classification. Is it a 1A? Is it a 2? Is it a 1BC? Whatever. Or is it, how far is it away? Like using redshift regression. So how far is this supernovae happening? And so we run the tests and we absolutely fucking bomb it. Like, this is the gray line is the baseline, and the orange one is Maven Light. This is the model that we produced. And yeah, I don't know, there's even like, it's not great. Also for the regression, for the other task that I mentioned, we're at least matching it, but we're not like, we're not doing fantastic. So I think, so this was a bit, this was somewhat unfortunate. So what did we do is simulations. In that case, we have simulated data. And we produce roughly 500,000 supernovae, and just let the computer completely grind away on that data and see what happens. And you ask yourself, well, this is not real data. Is there something called, does it look good enough? Is there distribution shift?
What simulations are these?
So I'm not the expert on that one, but I can get after.
But they're simulated spectrum?
The spectra, simulated spectra and photometric data corresponding to the same event. Plastic, it's called. It's not like a proper like 3D simulation. It's I think a more reduced physics model that produces these ones, but I understand. And so this one, if you heard of this name, this is I find these plots super beautiful. So what we're doing is like we have these like 100-dimensional representations of supernovae, which turns out are hard to visualize. So what you can do is like what you hope to is like create the same thing in 2 dimension and preserve all of the distances. Of course, that's mathematically impossible. So DSNE, DSNE, I don't know how to. I think there's like a GIF kind of thing going on. You can effectively at least try to project it down to 2 dimensions. And so the question is the distribution shift or not? And you can see like there's the ones that have a black ring. These are the observed ones, and the ones that don't have a black ring. are the simulated ones. And indeed, they're kind of different in the trained model. So they seem not to be, at least some indications that they're not at least super close. But let's look at actually what really matters is the performance of the model, and which is Maven now. And we're doing much better. We're still not matching, at least in classification, the baseline, but we're getting pretty close. And we're within error bar at least, not as terrible as before. And in redshift regression, we finally outperform after only 500,000 supernovae. But it's still, we still outperform, and this was pretty cool. Like, we were able to create effectively a state-of-the-art model that was able to take this data. But why is it so hard, right? Like, that has to do with where contrastive learning is good or not. That's what we realized afterwards. We would have liked to realize it before, but afterwards, is contrastive learning works well if you have two modalities that have like lots of mutual information, right? You have here pictures of this samoyed here, and you see a lot of dog in both of them. So the vectors that you're gonna learn from them are gonna really know about samoyeds. And for example, over here for the schnauzer, yeah, this is, both of them represent the same dog. There's lots of information in there, right? The same nose shape, maybe the eyebrows or whatever. So there's lots of information for the model to capture. But however, if you have, in the case where it doesn't work well, is say you have the picture of the dog and something, a description, right? Say like here, a cute dog sleeping. Like the only information that really kind of is useful is, okay, there's the dog, it's sleeping. There's not too much information that you can use for both of them. Similarly, here, a dog with a bow tie, like there's not too much information. I think the same thing happens with us. Spectroscopic is such a highly informative modality, right? There is like all of the classification you typically do with spectroscopic data. We look at the different lengths and determine whatever type it is, wavelengths, and so most of the information comes from the spectroscopic, and the photometric actually doesn't contain that much information. And so this was effectively the crux of our project. But we still were able, which in the end, looking at this one, makes it actually surprising that we were able, in the end, at least partially, to outperform the baselines. And likely we can do much better knowing that this one. So we're gonna now do an next iteration and hopefully further outperform these baselines. And so yeah, we were able to create a state-of-the-art foundation model. Simulated data works. That was surprising, even though it looks different, it still contributed to the performance. Needed a factor, but still. And we can do better. Like contrastive learning was probably not the best choice, but I think with some augmentations, we likely can further outperform and do much better. All right, I think that's my time. Any more questions about this? Or just...
Comments? Any other questions? Anybody online?
Sorry, for the verification of this project, were you running off of observed like photometry and redshifts, or was
all verification was on observed data? It was just the pre-training was on simulated one.
Maybe you need better simulated.
But that would be great. Can you provide me with 500,000?
No, but you can talk to, I don't know the code that you're using, but you could talk to the people who do TARDIS, which is, you know, this open source spectral synthesis code for supernova.
I see.
And they might be interested.
Yeah. We work with, you might know Alex Gagagliano. Oh yeah, he's one of the collaborators who was the one that hooked up us with the simulated data. And so that was, yeah, but okay.
But the discrepancy between the simulated data and the observed data.
Yeah.
You know, if you improve that, maybe.
Yeah, that would for sure help. That would happen. But likely what probably would help a lot too, what I think this is the next thing we try is well, in a way, contrastive learning is good at capturing mutual information, right? Information that is in both modalities. However, it sometimes there's still information that is just in one modality but not in the other. If we further can capture that specific information, we can probably outperform that further. But yeah, better simulated data would also be great. More simulated data, more compute, bigger computers. That's all.
Hi, really nice talk. I like your humor as well. So when you decided to use a contrastive model, I have a couple of thoughts about it in that the actual vector that you're minimizing, does it involve the data you're getting from the spectrum itself, or are you just trying to match the actual are you trying to match spectrum? Or are you trying to match the thing that you get, the information you get after you've analyzed the spectrum?
So after analyzed, yeah, okay, so I don't use any labels, right? So what I'm throwing in is purely the spectroscopic data and at contrastive learning and the photometric. It doesn't know anything about what supernova type it is, how far it doesn't know anything about this.
That's why I think the photometric stuff is so different from your spectroscopic data that I don't know how you would converge. Would it not make more sense to use like an adversarial network, where you use the spectroscopic you use the photometric modality to generate a bunch of spectroscopic data from a photometric
as an augmentation?
Yeah,
that would be a cool idea. Yeah. I mean,
that from the photometric, I could pretend I'm generating a spectroscopic structure and compare that versus the real ones I have.
Yeah, that might be an exciting idea. But the cool thing is, like, about these projects, like, I mean, you can just throw the kitchen sink at it, and as long as you get a better validation performance on the test data set, everything is pretty far. As long, of course, we are a bit more careful. We use here k-fold validation just to make sure that we're not just completely terrible things. But yeah, it sounds like a cool idea. Oh yeah, it would be you like any conditional generation. But yeah,
because my understanding is that like you're trying to extrapolate something from the photometric data.
I'm just trying to get I'm trying to be cheap, and if I can go further with my automatic data.
The classification is hard on photometric, but the redshift shouldn't be.
Yeah, redshift. Yeah, and that's kind of consistent. Like we suck at the classification, but we even outperform supervised baselines effectively, and yeah. Yeah, we were trying to cheat to see. Initially, we were like, "Oh yeah, maybe this is just magic," and suddenly we can.
How many colors do you have in the photometric?
It's R and G.
Only 2 colors.
Yes, only 2 colors.
Okay, that's really hard.
Okay, that's okay. I'm not the supernova person.
No, but when people do photometric redshift, they usually have more colors.
Okay, yeah. Yeah, we could.
I think for the
4 or 6.
the classifiers like salt too and whatever, you need. Two.
Yeah, this is all pretty. Wait, what's way to detect microphone? That's pretty well. Oh no, it's okay, well, it's still.
No, we didn't turn on the AI companion for the AI.
Oh yeah. All right.
Okay, well, anybody online have anything? There's nothing in the chat.
There's nothing in the chat.
Yeah, so good. Wait. Perfect.
All right, well.
That was very nice, Thomas.
Thanks
Thomas
again.
Again.